Hello, I am Dr. Sigar Kanti, Associate Professor of Mathematics, Government First Grade College, KR from Bangalore. In this video, I am going to discuss some more examples on isomorphism of graphs. Before that, I will go to one result here. I take this as a theorem. Two graphs G and H are isomorphic if and only if their complementary graphs G bar and H bar are isomorphic. Okay. So G and H are isomorphic if and only G bar and H bar are isomorphic. G bar and H bar are the complementary graphs of G and H respectively. Okay. So to prove this, so here given that G is isomorphic to H, right? Then number of vertices of G equal to number of vertices of H. Number of vertices, number of edges of G equal to number of edges of H. Okay. Now here, so that is here number of vertices of G equal to say P. Then number of vertices of H must be equal to P, and number of vertices of G bar is also equal to P. Number of vertices of H bar are also equal to P, because here G bar is the complement of G and H bar is the complementary graph of H. So therefore the number of vertices must be same. Now here let me consider G and H are isomorphic. So here let G is isomorphic to H. So here I will consider let UV be an edge in say G bar. Okay, UV is an edge in G bar. If UV is an edge in G bar, then this implies UV is not an edge in G. And if UV is not an edge in G, as G is isomorphic to H, F of V is not an edge in H. Okay, because G and H are isomorphic. And if this is not an edge in H, implies F of V is an edge in H bar. Okay. So here we have taken UV be an edge in G bar. Then we have proved that F of V is an edge in H bar. And if this is not an edge in G bar, we can prove that in the similar way we can prove that F of V is not an edge in H bar. Okay. So here we can write if and only if. Okay, if and only if. So this shows that G is isomorphic to H, then we can say that G bar is isomorphic to H bar. That is, this implies G bar is isomorphic to H bar, and conversely we can write. And conversely, that is, if G bar is isomorphic to H bar, then G bar complement is G. It is nothing but G. H bar complementary graph is H. Okay, so that is G is isomorphic to H, then G bar is isomorphic to H bar. Or conversely, G bar is isomorphic to H bar, then G is isomorphic to H. This is a result. Sometimes what we do, if it is very difficult to show that G is isomorphic to H, we show that G bar is isomorphic to H bar. Or in order to prove that G is not isomorphic to H, we try to prove that G bar is not isomorphic to H bar. Okay, I'll go to an example. Verify G. I'll write graph G as like this. This is a graph, and H is another graph. Okay. We can label here U1, U2, U3, U4, U5, U6, U7, U8, and here V1, V2, V3, V4, V5, V6, V7, V8. Okay. We have to verify these two are isomorphic. See here, what I do here is I will observe these two graphs here. See here 1, 2, 3, 4, 5, 6, 7, 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8 vertices. So number of vertices of G equal to number of vertices of H. No problem. And next, if I go to the edges here, see here degree of this is equal to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges are here. And here also we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, and this is 9, and this is 10. Here also we have 10 edges. And if we go to the degrees of the vertices here, one vertex is of degree 2, this is also degree 2. That is, there are 2 vertices, and here also we have 2 vertices. 4 vertices are of degree 2. Here 1, 2, 3, 4 vertices of degree 2. And this is vertex of degree 3, vertex of degree 3, vertex of degree 3, vertex of degree 3. And 4 vertices are of degree 3. Here also we have 1, 2, this is the 3, 4. 4 vertices are of degree 3. Okay. Degrees are also same. But G is not isomorphic to H. This is because, see, if you observe the graph, there is a cycle. Okay. U2, U3, U7, U6 is a cycle. And on this cycle, we have degree of this vertex is 3, degree of this vertex is 3, degree of this vertex is 3, degree of this vertex is 3. Now, if you go to graph H here, we have cycles of length 4 here. So, this is cycle of length 4 here, but degree of this is 2, degree of this is 2, right? And 1, 2, there is no cycle of length C4 such that all the vertices on that cycle have degree of 3 in H. Or we can say like this also. See, this is a vertex. V1 is a vertex of degree 2. And this is adjacent with degree 3, adjacent with a vertex degree 3. And here there is a vertex. This is a vertex here. Okay, this vertex is, yeah. If you consider the degree 2 vertex, U1 is a vertex of degree 2. This is adjacent with vertex of degree 3 and 2. And U4 is a vertex of degree 2 adjacent with vertex of degree 2 and degree 3. And this is also a vertex. This is also U5 is also a vertex which is adjacent with vertex of degree 3 and degree 2. And U8 is also a vertex of degree 2. This is adjacent with the vertex of degree 2 and adjacent with the degree vertex of degree 3 here. So here we have, there is a vertex V1 which is adjacent with 2 vertices V2 and V4, and these two have degree 3. But here if you consider U1, U4, U5, U8, these are vertices of degree 2. They are not adjacent with the vertices of degree 3, that is adjacent with the vertex of degree 2 and degree 3 here. So therefore here these two graphs are not isomorphic. So we can write the reason like this. In H there is a vertex, say V1, which is adjacent with vertices, so that V2 and V4 of degree 3. But in G, if you say verify for this vertex or for this vertex or for this vertex or for this vertex, these are the 4 vertices of degree 2 and they are adjacent with one vertex of degree 2 and one vertex of degree 3. So and that here we write no such vertex exist in G. Therefore, we can write G is not isomorphic to H. Okay. Next, I will go to another example. Verify G. I will take G as this is our G, and H is okay. I will take this as A, B, C, D, E, F. Here I will take 1, 2, 3, 4, 5, 6. These are the 2 graphs. And if you observe, G consisting of 6 vertices, H also consisting of 6 vertices. And degree of each vertex in G is equal to 3. Here also degree of each vertex in H is also equal to 3. But these 2 graphs are not isomorphic. How? We can give one reason here. See, in G, there are vertices A, B, F. Okay. These are 3 mutually adjacent vertices. That means here there is a triangle in G. But if I go to H, no such triangle exists here. If you go with 1, there is no triangle. If you start with 2, there is no triangle. Start with 3, no triangle. 4, no triangle. 5, no triangle. 6, no triangle. This is one reason we can say that G is not isomorphic to H. So that is here. G has a triangle A, B, F, but H has no triangle. So therefore we can say that G is not isomorphic to H. Okay. Next, I will go to another example. G 1, 2, 3, 4, 5, and within this I will take one vertex 2, 3, 4, 5. Join these vertices, and then join these two. Okay, this is our G. And I will take one more graph here. Write a triangle. On the edges I will take vertices here, and in the middle I will draw one more vertex here. Join these vertices and take some vertices on these lines here, and join the edges, this vertex to this vertex, and this vertex to this vertex, this vertex to this vertex. Okay, this is our H. Now G consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. H consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. Both have same number of vertices. And degree of each vertex in G is 3, 3. So degree of each vertex in G is 3. Here also degree of each vertex in H is also 3. Right? That means your number of vertices are equal, number of edges are equal, degrees are same. That is, both are 3 regular graphs. We have to verify whether G is isomorphic to H or not. For that, we have to verify the adjacency. So for that, what I do here is, first I label the vertices of G as U1, U2, U3, U4, U5 like this. Okay, right, U1, U2, U3, U4, U5. Then I will U5. I take this vertex as U6, and this as U7. This is U8. This is U9, and this is U10. Okay. Now I want to assign the label the vertices of H in this manner. So here this is U1. I will take this vertex as the corresponding vertex of this. That is U1 corresponding to V1. I will label this as V1. And here U1 is adjacent with U2, U7, U5. So therefore I will write this as V2, V7, V5. Okay. U1 is adjacent with U2, U5, U7. V1 is adjacent with V2. Okay. V2, V5, V7. Then see, U2 is adjacent with U3 and U8. U3 and U8. So I write this as U8. Okay. I will take this vertex as V3. Okay. This vertex as V3 and one more vertex. This vertex as V8. This is our V3 and this vertex as V8. Okay. V8. Now coming to U3. U3 is adjacent with U9, U4. Okay. So I have to label two vertices as U9 and U4, which are adjacent with V3. So V3 is here, and already I have taken this adjacent is here. I have to take this vertex as which one? U3 is adjacent with U4 and U9. Okay. I have to take this U4 and U9. If you take this U4, we have to keep in mind that V3 is adjacent with V4, and that vertex must be adjacent with U5. Okay, U3 is adjacent with U4 and U4 is adjacent with U5. Here also we have to take V3 is adjacent with V. If I take this as V4, V4 is not adjacent with V5. Therefore, I will take this vertex as V4. Okay, this vertex as V4, and this vertex as V9. This is V4, and this is our V9. And I think only one vertex is remaining, or two vertices are remaining. Okay. Next, from V4. Here we have U4 is adjacent with V3, V5. Okay, this V4 is adjacent with V3, V5, and here this U4 is adjacent, U10 is there. So therefore, I'll take this vertex, this middle vertex as V10. Write this as V10, and only one vertex is remaining, I think. This V1, V2, V3, V4, V5 is there. V6 is not there. V7, V8, V9, V10. So therefore, I will write this vertex as V6. Okay. Now, I will redraw this graph. And if the resulting graph is same as this graph, then we say that these two are isomorphic. So how to redraw? I will write the points here. I will take this point as V1. and I will take this as V2. I will take this point as V3, and this is our V4 and V5. I will take here V6. I will take here V7. Here we take V8. One more vertex V9. Another vertex V10. Okay. So first we have taken the vertex. Then I will add the edges. See, V1 is adjacent with V2, V7, V5. V1 is adjacent with V2, V7, V5. And V2 is adjacent with V1 already we have taken. V2 is adjacent with V3 and V8. V3 and V8. This is V3 and this is V8. And V3 is adjacent with V2, V4, V9. Already we have taken this. Okay. V3 is adjacent with V4, V9. V3 is adjacent with V4 and V9. Next. V4 is adjacent with V3, V10, V5. So V4 with V5 and V10. V4 with V5 and V10. Okay. Next, V5 is adjacent with V1, V4 already we have written. Then one V4, V1, V4, V6. Okay, I have to add this edge V5 to V6. V5 to V6. Next, P6 is adjacent with V5 already written. Then I have to add this V6, V8, V6, V9. V6 to V8, V9. V6 to V8, okay, V9. And then V7, coming to V7. V7 is adjacent with V1 already written. And then V9 and V10. So V7 to V9, V10 I have to write. V7 to V9, V10. What about V8? V8 is adjacent to V6 already drawn. V2 already drawn. I have to add this edge. V8 to V10. V8 to V10. V8 to V10. And what about V9? So V9 is here, it adjacent with V7 already written, V3 already written, V6 already written. And V10 is here, it is adjacent with V4 written, adjacent with V7 written, adjacent with V8 already written. So we can draw this graph as this type. And if you observe these two graphs here, these two graphs are same here. So therefore here we say that G is isomorphic to H. Here we can write G is isomorphic to H. So we can define a function from vertex set of G to vertex set of this here such that f of ui is equal to vi. u1, u2 is an edge. Here corresponding v1, v2 is an edge. So here we write G is isomorphic to H. Next I will go to another example. I take the same Peterson graph but other graph is some different. Next example. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Within that we write 5 vertices. Joining these vertices, and then this edge, this edge, this edge, this edge, this edge. This is Peterson graph. Okay. This is our G. Next I will write one more graph H here. 1, 2, 3, 4, 5. Within that I will write one more cycle here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And joining these edges, vertices. Okay. So this is our H, this is our G. See here G consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. Here also we have 5 plus 5, 10 vertices. and degree of each vertex in G is 3, 3, 3, 3. Every degree of each vertex is 3. Here also degree of each vertex is 3. So that means number of vertices in G equal to number of vertices in H, number of edges in G equal to number of edges in H, but these two graphs are not isomorphic. This is because just we can give one reason. In H there is a cycle of length 4. So this is I will take A, B, C, D. See here A, B, C, D, E, A. This is a cycle of length 4. Right? This is the cycle of length 4. And if we go to G, if we go to G here, there is no cycle of length 4. If we start with this vertex here, 1, 2, 3, okay, 3, 4. If you come to here, 4, but there is no edge here. So that is here, there is no cycle of length 4 in G. There is a cycle of length 4 in H. Okay. So therefore, we say that these two are not isomorphic. So that is here, there is a cycle of length 4 in H, but not in G. So therefore, we say that G is not isomorphic to H. Okay. So that is here we have A, B, C, D, A. This is the cycle of length 4. But here there is no cycle of length 4. We get length 5 are here. But length 4 cycle is not there in G. Therefore, these two are not isomorphic. I'll go to another example. Verify G. We'll take a graph with 1, 2, 3, 4, 5, 6, 7, 8. Graph with 8 vertices. Joining these, make a cycle, and then join this one, this one, this one, 1, 2, 3, 4, 5, and coming to this vertex, leaving this and this, I'll go to 1, 2, 3, and coming to this vertex, 1, 2, here I write this edge, this edge, this edge. Next, coming to this vertex here, 1, 2, add this edge, and this edge. Coming to this vertex, next vertex, 1, 2, adding this edge. Next, coming to this part, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah. This is a graph with 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8. And degree of each vertex is 5 here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Degree of each vertex is 5. This is a graph G. And next I will write one more graph here, H. Again 1, 2, 3, 4, 5, 6, 7, 8. Make a cycle first. And then I'll add some more edges. Adding these two. And then one more edge here. Edge, 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 and adding the opposite vertices, adding edge to opposite vertex, 1, 2, 3, 4. See, this is the graph. 1, 2, 3, 4, 5, 6, 7, 8 vertices. Here also we have 8 vertices. Here also we have 8 vertices. And the degree of each vertex in G is 5. Here also degree of each vertex is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Yeah. Degree of each vertex is 5. That means here number of vertices in G is same as number of vertices in H. Number of edges in G is same as number of edges in H. And degree of each vertex is same here. That is, both are 5 regular graphs. But even then, these two are not isomorphic. So in this case, it may become difficult to verify the adjacency from G to H. What I do here is, I will draw the complement of G and I will draw the complement of H. If G bar and H bar are isomorphic, then we say that G and H are isomorphic. Or G bar and H bar are not isomorphic, then G and H are not isomorphic. So for that I will label this A, B, C, D, E, F, G, H. Here also I will write A, B, C, D, E, F, G, H. First I will draw G bar. Okay. In G bar, 1, this is A, B, C, D, E, F, G, H. Okay. 8 vertices. See here, A is adjacent with B, A is adjacent with B, not with C. Therefore, I have to add AC in G bar. So, I will find out the non-adjacent vertices here. AC and AG. AC and AG I have to add. AC and AG. Next from B. B2, BD, BD and BH. I have to add BD and BH. BD and BH. Okay. Next from C. C2, C2, CA already I have written. C2E. I have to write C2E. C2E. Okay. Next from D. D2, DA already we have written. DG I have to write. DG. DG. Okay. DG. Next. From E to B I have written. E sorry, is here. E2 is non-adjacent with E, adjacent B is not adjacent to C. This already we have written. E to G, E and G are non-adjacent. Therefore, we have to add EG here. EG. Okay. EG. Oh, I'm sorry. I think A2 C and A2 C and G. A2 C and G we have written. B2 D and H. B2 D and H. Yes, we have written. From C, C2 A and E. C2 A and E we have written. Okay. From D to B, D to F, not D to G. Yeah, D to F I have to write. D to F. And E to C we have written. E to G I have to write. E to G. Okay. E to G I have written. Next F. From F to FD I have written. FH I have to write here. FH. F to H. And from G to A I have written. G to E I have written. From H to B written. H to F also written. So this is our G bar. Okay, this is our G bar. And here, this G bar consisting of, see here, this is one, see, this is the square, that is cycle of length 4, and one more square is here. This is also cycle of length 4. That is, two disjoint cycles are here. We can write this G bar like this. G bar can be written as like this. Okay, two disjoint cycles of length 4. Okay, this is our G bar. And coming to H bar, let H bar. Again, 8 vertices are here. I write A, B, C, D, E, F, G, H. Right? Now, I have to add the edges from A to where I have to add. A to B, no. A to C, no. A to D, I have to add. AD and AD and AF. AD and AF. AD and AF. Okay. Next from B. B2. Where to add? B2, C, no. B2, D, no. BE. BE and BG. BE and BG. BE and BG. Okay. BE and BG. Next from C. C2. B, no. B, no. A. C2. C2. CF. CH. CF. CH. CF. C2H. Okay. CH. And then D. D2. DA already I have written. Then D2 G, DG. Okay, DG. I have to write DG. Next, from E. E to EB I have written. EH I have to write. EH. E to H. E to H. Okay. Next, from F. F to C I have written. F to A also written. From G. G to B. GB is written. Okay. GB is written. And then GD is also written. GB is also written. And from H, I think we have written here. From H, I have to write H is adjacent in H bar. H is adjacent with E written. H is adjacent with C also written. So this is our H bar. And I can write this H bar as, see here, A, start with A, D, G, B, E, H, C, F, A. That's why I am getting a cycle of length 8 here. We can write this graph as 1, 2, 3, 4, 5, 6, 7, 8. This is our A to A, D, D to G, G to B, B to E, B to E, E to H, E to H, H to C, C to F, okay, and F to A. So that is here, there is a cycle. There is a cycle of length 8 in H bar, and here in G bar we have two disjoint cycles. So that is here, G bar is not isomorphic to H bar. Therefore, G is not isomorphic to H. So here we write G bar is not isomorphic to H bar. Therefore, we can write G is not isomorphic to H. Okay. Thank you. I will stop here.